last class we were discussing about dielectric materials, and we were considering what happens when an external field is applied to a dielectric material. We saw that when the external field is applied to the dielectric, we can model the dielectric as being consisting of dipoles. That is, dipoles are introduced or induced inside the dielectric material, and these dipoles in turn will generate an electric field of their own. We saw that we could actually relate this response of the material, right, in terms of its polarization to the electric field. If you recall, the dielectric material, when it gets polarized, the degree of polarization depends on its polarizability. If the material is made up of a single type of atoms, then we calculated what is the polarizability of this particular atom. If the atom has a radius r, okay, then the polarizability is proportional to r cube, and it is most importantly it is proportional to the linear of the electric field. That is, the polarizability is linearly proportional to the electric field. Similar to this atomic polarization, there is ionic polarization, in which the ions inside the material gets polarized. There r needs to be replaced from the atomic radius to the ion radius. Right? After this, we started talking about oriental polarization. Oriental polarization, we actually started describing the expressions for that one. We found that oriental polarization actually is inversely proportional to temperature, and for small values of a certain quantity called A, which was E by kT, for small values of PE by kT, we found that the Langevin function through which we had defined the oriental polarization can be replaced by a simple expression of A by 3, and thus write down the expression for alpha orientation or alpha oriental polarization as P square by 3 kT, right. So this was the oriental polarization, and now if you assume that there are a lot of these molecules, each of them getting polarized according to this polarizability function, then you can write down the total polarization P as that of P square NE divided by 3 kT, where E is the electric field, right, N is the dipole density, that is the number of dipoles per unit volume, and P is the dipole moment. Therefore, P into N would actually become the net dipole moment density. Of course, we are interested in polarization per molecule, which turns out to be simply P square E by kT. Again notice 3 kT, notice again the linear dependence of the polarization on the electric field. Thus, we have discussed three kinds of polarizations or polarizability expressions. One was atomic polarization, the other one was ionic polarization, and the third one was oriental polarization. Amongst these three, atomic and ionic polarizations are temperature independent. Okay. However, oriental polarization is actually dependent on the temperature, and in fact it is inversely dependent on the temperature, meaning that as temperature T increases, this corresponding quantity P square by 3 kT actually decreases, which means simply that as temperature has increased, the kinetic energy that these atoms or molecules inside dielectric material, that the kinetic energy of these molecules would actually increase, and therefore it becomes extremely difficult to align them to a particular direction, right. Oriental polarization was how you could align into a particular direction, and that alignment actually becomes a problem as you increase the temperature. Okay. So we can actually combine all these three polarizations and write down an expression for polarization. Remember, this polarization vector is denoting the amount of dipole moments per unit volume. It is essentially the volume density of the net dipoles that are present inside the dielectric. So this P will be equal to the number of elements that you have per unit volume times alpha E, standing for electronic or atomic polarization, atomic polarizability, alpha I standing for the ionic polarization. You could replace alpha E or alpha I appropriately when you are considering either electronic polarization or ionic polarization, okay, plus the oriental polarization that we discussed. Luckily for all of us, the polarization vector, this one, the amount of net dipole moment per unit volume is actually linearly proportional to electric field. In fact, this is typically given by a different name called chi E. This chi is a Greek letter and this E just stands for electric field susceptibility, because we will be seeing a similar parameter when we discuss magnetic fields and magnetization inside a material, inside a magnetic material. For now, this subscript E denotes that this material is dielectric, and this chi is actually what we call as susceptibility. Susceptibility simply means that how susceptible my dielectric material is to the external electric field. Okay, so that is what susceptibility means, and the larger the value of susceptibility, the more easier for us to polarize this particular dielectric. So P is epsilon 0 is the permittivity of the free space. This is included so that the expressions become simplified later on. So this P is epsilon 0 chi E times electric field. Since electric field is a vector, P also becomes a vector. So you have a vectorial relationship of polarization being directly proportional to electric field vector. Okay. For free space, chi E is equal to 1. So chi E, the susceptibility for free space, is equal to 1. For all other materials, this chi E is typically greater than 1, indicating that the polarization vector P would be greater than the free space value of epsilon 0 E. Okay. Now, what is this electric field? Was it actually the external field that we applied? Actually, it turns out that this is not completely the external field, because there are these dipoles which have interacted. So there is some amount of back action that has happened because of the dipoles that are generated, and this electric field E should actually be the field that is inside the dielectric. That is, inside the dielectric there is some back action because of the dipoles, because of the molecules, because of the ions that have changed their equilibrium positions as we have applied the external field. Therefore, this electric field is the net total electric field after taking into account all the back action. It just turns out that this back action is so small that for most practical purposes we can neglect that, and this electric field will be the field that is generated because of the dipole itself, okay, or dipoles inside the dielectric itself. Okay. Now let us imagine that we have a dielectric material. Okay, so this is my dielectric material of arbitrary shape, and inside this dielectric material there are a lot of dipoles that are induced because of the applied electric field. Now let us calculate what is the electric field at some point P. Okay, this is the field point that I am considering at some point far away from the dielectric material. Okay, and let us say we write down this field point vector. We can denote this by a particular vector r prime with respect to the origin, and we will use first the idea of obtaining the potential, and from potential we will try to determine the electric field. That is the easier way of proceeding in this problem, because potential is a scalar function, and obtaining a vector from the scalar by the gradient operation is actually much simpler than trying to estimate electric field directly. Okay. So let us assume that we have a small volume inside the dielectric that we are looking at, and this volume has a differential volume of dV prime, and it is kept at a certain position inside the dielectric material. I mean, actually we are not putting any volume, we are just assuming that we are actually carving out a small volume for our consideration of finding the electric field. Okay, so we just imagine that there is a small volume inside the dielectric, and then this we want to calculate what is the potential because of the dipoles inside this volume on the field point P. Okay. So if you look at this, there are dipoles in this differential volume dV prime, and we want to calculate what is the potential at the field point. After we have calculated the potential, we will then calculate the electric field. Okay. So how do we do that? Well, I know this is r prime, this is r. Okay. So let me get back to the same notation up here. This is r prime, indicating the source of the charges, and in this case charges are the dipoles that have been induced, and r is the vector from origin to the field point. Now the potential is actually a function of r minus r prime, or the distance between the, if these are the vectors, then r minus r prime, let us call this as capital R. Okay, So this r being the magnitude of the distance between the dipoles in the volume to the field point. Okay, so the potential is basically whatever the charges that are present inside this volume element divided by 4 pi epsilon 0 into r, right. We will use capital V for the potential and small v for the volume. Okay, so the potential at the field point, okay, the field point is at some point r, right. So this is at a vector point r. The potential at this point is actually given by 1 by 4 pi epsilon 0. Epsilon 0 is a constant, so we are going to take this outside. And then what is the total charges that are there inside this volume element? This charge density is actually P times dV prime, right. P is the polarization or the net dipoles per unit volume. Multiplying that by the volume element will give me the net dipoles sitting inside this volume element dV prime. So this would be the total charge that I have. Now P is a vector, so I need to actually rewrite this equation in a proper way and write this one as dot r hat divided by r square. Okay. Why is this 1 by r square? If you recall what is the field of a dipole, you will remember that if you considered two charges, one minus q and the other one at plus q, and this defined qd as the dipole moment, right. At any other point where we were trying to find the field, we found that the field is actually p dot r hat divided by r square. The field was proportional to p dot r by r square, where p is equal to qd was the dipole moment, right. So this is dipole moment field is actually 1 by r square. Therefore there is a 1 by r square sitting here, and r is a unit vector in the direction from the source charge to the field point. However, we will assume that this field point is kept at a very large distance. Now that is how we actually wrote down this field for a dipole earlier, right. So we assume that the dipole itself or the dielectric material itself is confined to a small region. In other words, this r prime magnitude is very small compared to the magnitude of r. Okay. This is kind of quite realistic in many cases that we will be considering. Therefore, we can make this approximation and obtain that the potential is actually going as 1 by r square. Okay. So this is the potential. We should also write down what is the expression for r. In order to write down that, let us choose Cartesian coordinate system. So in the Cartesian coordinate system, r prime, the source charges, is described by the vector x prime x hat plus y prime y hat plus z prime z hat, and r, the field point vector, is defined as x x hat plus y y hat plus z z hat. Note that you could have actually done this entire calculation that we are going to do without really getting into one particular coordinate system. It's just that it kind of simplifies our initial intuitive understanding of the field that we are about to calculate. Okay. So if you want, you could completely eliminate a particular coordinate system and work directly with the expressions that we have used here. Okay. That seems to me to be slightly not intuitive. Therefore, we are going to introduce some coordinate system, but the results that we obtain will be independent of the coordinate system. Okay. So we have r is equal to x x hat plus y y hat plus z z hat. So clearly the vector r will be x minus x prime x hat plus y minus y prime y hat plus z minus z prime z hat, and the magnitude vector r will be x minus x prime square plus y minus y prime square plus z minus z prime square, all under square root, right. So this is the expression for r, and what you want is r square. In order to obtain r square, you can remove the square root or square on both sides and you will obtain r square. Okay. Now we will have to introduce one vector identity. We will actually give you how to derive that vector identity. See, I have inside the integral a quantity r by r square. Okay. This quantity is actually related to this quantity, gradient of 1 by r. Now gradient 1 by r is definitely a scalar function. So this kind of might look okay because there is a scalar and onto the left hand side there is a vector. So gradient operates on a scalar, gives you a vector, that might be alright. However, what is this prime on the gradient operator? We have not talked about prime on the gradient operator. It just turns out that this prime simply indicates that you have to differentiate with respect to the primed coordinate system, that is x prime, y prime, z prime coordinates, rather than the unprimed field coordinates, which is x, y and z. So del prime is defined as x hat del by del x prime plus y hat del by del y prime plus z hat del by del z prime. Okay. Now you can try and find out whether this equation is true or not by writing 1 by r as x minus x prime whole square plus y minus y prime whole square plus z minus z prime whole square to the power minus half, right, that will be 1 by r. And now applying the gradient operation, so amongst the gradient operation let us first apply only del by del x prime, let us differentiate this one with respect to x prime and then find out what would be the resultant expression, and we will be able to find the expressions for del by del y prime and del by del z prime very easily, right. So let me differentiate this one with respect to x prime. What do I get if I differentiate this one with respect to x prime? So I have del by del x prime, this quantity y minus y prime square plus z minus z prime square will be a constant, right. When I am differentiating with respect to x prime, it would be a constant. So if I look at what is del by del x prime of 1 by x minus x prime square plus some constant, let us call the constant as k square, okay. Why it is constant? It is constant simply because when I am differentiating with respect to x prime, y prime and z prime are constant, okay. So this is a half up there. Now you can actually differentiate this one using the basic rules of differential, and you are going to get x minus x prime divided by x minus x prime square plus this constant square, constant we will write it down is y minus y prime square plus z minus z prime square. In place of half it becomes 3 by 2 now because there is a differential, right, and there is x minus x prime. In which direction will this be pointing? It would be along x prime. So if I differentiate and then look at the gradient along the x prime, that is the component along the x prime, I am going to get this x minus x prime x hat divided by this quantity to the power 3 by 2. Now there is no big surprise here that if I try this one with y del y prime and z hat del by del z prime, these quantities would also give me very similar results of y minus y prime y hat and z minus z prime z hat, okay, and the denominator will still be the same, it will not change, right. It would be x minus x prime square plus y minus y prime square plus z minus z prime square to the power 3 by 2. Now collecting all these three terms, you can see that del prime of 1 by r is actually given by x minus x prime x hat plus y minus y prime y hat plus z minus z prime z hat divided by this fellow in the denominator, which is x minus x prime square y minus y prime square plus right, and you can easily see that this equation, I mean this expression of the vector that we have on the right hand side is nothing but r minus r prime divided by r minus r prime magnitude 3 by 2, which is, you know, after you factor out r minus r prime, you can write this as r hat divided by r square, where r is the vector r minus r prime, right. So we have shown the equation that we wanted to show, that is r prime by r square is actually del prime of 1 by r, gradient of 1 by r. Now what good is that equation for us? Well, look at this expression here, right. Look at this expression here that we have. I have r prime by r square, I can replace that r prime by r square by this gradient prime of 1 by r, right. I am going to do that one now. After I do that, I get the potential V as 1 by 4 pi epsilon 0, the constant outside, and inside the polarization or the net dipole moment P dV prime dot gradient of 1 by r, gradient of 1 by r. Well, that is it, the r square has been absorbed in this gradient, correct. Now we might want to use or we will be using another vector identity, and that vector identity is gradient prime of 1 by r into p. Okay. So, not the gradient, the divergence of this one. Okay. So, I am hoping that this is visible to you guys. So, this is the gradient, right, sorry, this is the del operator with respect to the primed coordinates. So, del prime dot 1 by r p, p is a vector, 1 by r is a scalar, right. So, if I have a scalar f and a vector g, okay, so if I have a scalar function f and a vector field g, then del dot of fg is actually f del dot g plus g dot gradient of f. Does it make sense? Yes, it makes sense, because this is a divergence operation on a vector field. Just because I am multiplying the vector field g by a scalar function f does not mean that I have changed this into a scalar field. So, this is actually a vector field. So, divergence of this vector field will be equal to f times del dot g. This is all right, because del dot g is a scalar. So, scalar times scalar will still be scalar, and gradient of f is a vector, g dot gradient of f will become a scalar, right. So, I have this identity and I can apply this identity to 1 by r into p. Okay. So, if I apply this identity, what do I get? I get 1 by r del dot p. Now, this del is with respect to the primed coordinate. So, therefore, this is del prime dot p, and this is nothing but p dot gradient prime of 1 by r. Now, if you look at this second term, this is precisely the term that is sitting inside this volume integral. dv prime is just a scalar that can be taken out without any change in this expression, right. So, dv prime can be just put outside, and then you have just move it outside of this term, okay, it's outside of the dot product, I mean. So, you have p dot gradient prime of 1 by r, and that gradient can be written as, I mean that expression can be written as del prime dot 1 by r p minus 1 by r del prime dot p. So, if I make that substitution, I can write down for the potential V of r, I can write this down as 1 by 4 pi epsilon 0, there is an integral, and this becomes gradient prime dot p by r, right, 1 by r into p is p by r over the volume minus 1 by 4 pi epsilon 0, the second term is del prime dot p divided by r, right, because this is 1 by r times del prime dot p. So, that is up here integrated over the volume. The volume integral is actually over the dielectric, that you should keep in mind. Okay. Now, from here we can sort of apply couple of other theorems. I know how to apply Gauss's divergence theorem, so that I can convert this del dot integral into a surface integral, right. So, I can apply divergence theorem here. So, I will apply divergence theorem. So, if you are confused what a divergence theorem is, integral of d dot ds is actually equal to integral of del dot d dv, right. This is the Gauss divergence theorem. Surface integral can be converted into volume integral. Here what I have is a volume integral, therefore, I can convert that into a surface integral. So, this becomes integral of p dot ds divided by 4 pi epsilon 0 r, right, and this integral must be closed over the surface that is that the dielectric material is bounded in. So, the dielectric material is bounded by a surface S, which is what we are considering, and therefore, this volume integral can be replaced by the surface integral. This let us not change anything. So, I still have del prime dot p divided by 4 pi epsilon 0 r dv prime, correct. Now, this kind of starts looking very suspicious, like a surface charge density and a volume charge density, correct. This first one, which is p dot ds by 4 pi epsilon 0, could very well be obtained by an equivalent surface charge distribution. We will call that as rho sp, which is this surface charge because of the polarization, and 1 by r indicates that is the potential function, right. So, this kind of looks like a potential that could be developed or that could be induced because of a surface charge density, an equivalent surface charge density, and that equivalent surface charge density is rho sp. Okay. Similarly, if I look at this del dot p, right, this could be a volume charge density. If you go back to that Gauss's law, integral of del dot d, I mean Gauss's law in point form, del dot d is equal to rho, this kind of indicates a volume charge density, and that volume charge density would be say rho Vp. Of course, it is possible to incorporate the surface charge into volume charge, right. So, you can always define a volume as a vanishingly small height with a finite area and include surface charge into volume charge distribution itself, in which case you will have only one volume charge, equivalent volume charge. Okay. We can do that, and that is what is normally done. Okay. So, I have a volume charge and the surface charge, and please note that I have put in a subscript p here. Okay. In addition to the usual S standing for surface and V standing for volume, I have put in additional p here to indicate that these charges are not the charges which are freely available to you, but they are the charges because of the polarization. That is, the material has been polarized and these equivalent surface and volume charge densities are available, but they will act as though they are free charges and produce an electric field. Now, you might be rightly asking, are these free charges available to us? Yes and no. Yes, in the sense that you can actually devise measurement on an atomic scale, okay, and these charges will be available to you. But we are considering phenomenon which is not such microscopic scale. We are considering phenomenon over macroscopic situations. You know, I take a lens, for example, which would be a dielectric media, and I don't want to put an ionic or an atomic measurements inside and try to find out this or try to access this surface and volume charges. Okay, I'll be happy as long as I am given a equivalent description. Okay, so I am not looking to actually extract the surface or volume charges. If I choose to, I can, but that is not the goal of our study. So for us, these are not available as free charges, rather they are bound inside the material. Okay, so these are sometimes called as bound charges, just to emphasize the fact that they are bound to the material. They are not available as free charges, at least on the macroscopic scale.